So the first question on the exam is, what carbon atoms in the unsubstituted ring of this guy are going to be the fastest to undergo nitration? There's two ways of looking at this. One is looking at, since we have this electron donating group here, we can look at where he is most likely to push the electron density, and therefore the most nucleophilic sites on our ring. And do note that we are only looking at this ring here, we're not looking at this one. So we can look at where this guy can push a negative charge into this ring, or we can take each of the 4 carbons in this ring, because obviously these two are not going to react. They're fully bonded, 4 bonded, no H's to remove, can't react there. So we can look at where each of these 4 carbons attacking an electrophile and see which one gives us the most stable carbocation. My personal favorite out of these two is to look at where the electron donating group is going to push our electron density. So let's start there. And of course, you should be recognizing this guy as an electron donating group because he has electrons on the atom that is directly attached to our aromatic ring. So, let's push some arrows down into the ring here. You can't see the color at all. Okay. Push some arrows down into the ring. And we make a bond here, which means we have to break a bond attached to this carbon. That bond is going to be our double bond here. And since what we're looking at is our relationship to this ring over here, I could bounce this here, but for the purpose of expediency, let's just push it all the way over to the ring over here. Make a bond here, which means you have to break a bond. We're going to break this bond. You can bounce right there. So that gives us our first resonance structure. Keep track of your charges. Our oxygen, we used a lone pair, so he should be positively charged now. And we just pushed a lone pair right here, so he should be negatively charged. You can also look at it in that our original structure was uncharged. Our final structure, our resonance structure, should have the same net charge. Plus and minus cancel each other out. So, this shows us, with his labeling of the carbons as 5, 6, 7, and 8, that 8 is going to have a minus charge on it. Which means that 8 is going to be nucleophilic and is going to fairly rapidly undergo nitration. Where else can we push these electrons? So if we go back to up here, and we decide to not have him jump onto carbon number 8, we'll have him jump over to the next position. Have to break a bond because we made one. That's going to push our electrons right here. So what does that give us? Oops. So you might notice that I'm in the habit of just kind of drawing bonds. We realize that we broke this one and we broke this one, but we made one here. So we should have a minus charge right here as a lone pair. So under his naming of these carbons, we've got carbon 5, carbon 6, carbon 7, and carbon 8. We've put a minus charge on carbon number 6, which means carbon 6 is our other carbon in this secondary ring here that is going to undergo nitration fairly rapidly. And that's essentially your answer. You can keep pushing the arrows if you want and you'll see that you can never get it to go on 5 or 7, which means that 5 and 7, it's going to take a bit of hammering to try and get them to undergo nitration. Where the ring wants to undergo nitration is carbon 6 and carbon 8. Second question. Explain how you distinguish between each of the pairs of compounds using each of our spectroscopic methods. First compound. Well, with any of them, my place to start with this is just to go through and get an idea of what precisely you would be looking for each molecule in terms of number of signals and splitting and integration and all that. So I like to set out kind of a chart layout of this. I'm not sure precisely how much space you had for this question on the exam, but if you don't get a lot of space, practice writing small. So, this guy here, we've got a little bit of symmetry going on right here, where these two methyl groups are going to be the same thing. So, that's going to give us one signal that integrates to 6, and as a splitting of a singlet. No hydrogens here. We got 2 hydrogens here. They are going to be coupling to this CH3 over here, which means they're going to be a quartet. So integration of 2 as a quartet. And of course, this methyl group over here, integration of 3 with a splitting of a triplet. And I presume at this point that you know where I'm getting these splitting values from. Neighbors plus 1 and all that. We can talk about the OH if you want to. Notice that between the two compounds they both have an OH, so that's really not going to be any different. And we're not talking, he doesn't tell you whether we're doing this in a protonated solvent or not. So you have enough data, I think, without the OH to try and tell the difference between these two, because the OH is perhaps not going to be as much help as it might. Moving into CNMR. Again, these two methyl groups are going to be the same thing. And this guy's going to be his own thing, this guy's going to be his own thing, this guy's going to be his own thing. So that means that we have 4 different signals here. You can get into where precisely they're going to show up, but that level of fine-tuning is not overly important here, as we'll see. So, we're going to say we have got 4 signals. IR, we've got an OH. That's really all we can tell, that's really all we care about right now. So, second molecule here. We have a plane of symmetry throughout the entire molecule, rather than just a localized symmetry like we had up in the first one. Which means we only need to look on the plane of symmetry into one side of it. We've got a CH3 here, 2 H's here, and an H sticking off here. That's going to give us 3 total signals, like we had for the other one, but perhaps they're going to be a bit different. So, starting with this guy here, he is going to have an integration of 1, and he is going to be not a triplet, he's going to be a quintet, because he does have a total of 4 neighbors. They're all the same, so they wouldn't couple to each other, but they are going to couple to him. These guys, 2 hydrogens. Don't be tempted to say that this is going to have an integration of 2, because remember our plane of symmetry. These guys are going to have an integration of 4. And what is their coupling? Well, let's just say that this neighbor is going to be about the same as this neighbor, and you can say that maybe they'll be a quintet. Or, if you want to be a little bit more specific, they are going to be a doublet of a quartet. And our methyl group, again, not going to be an integration of 3, it's going to be an integration of 6 because of our plane of symmetry. And what is he going to show up as? Is he going to show up also as a quintet? No, because each individual methyl group is only seeing 2 hydrogens. He's going to show up as a triplet. CNMR, plane of symmetry, we have 1, 2, 3 types of carbons. 3 signals. And for our IR, we also have that OH, and again, there's really nothing else interesting about all this. So, what are our major differences? IR, don't got much. So, no real difference between IR, and you can say that using IR, it's not going to be extraordinarily easy to distinguish these two. You'll see if you go on to other levels of chemistry that there is ways to tell these apart, but it's all, most of it down in the fingerprint region. So, CNMR. This is a fairly distinct difference here. We got 4 signals versus 3 signals. Just write that down. That should be good enough. HNMR. Personally, I would just write all of this stuff down, that for this guy you'd expect these, and for this you'd expect this. If you want to pull out individual signals, you can say that you're going to have this guy, very distinctly, integration of 1 is a quintet. You don't have anything in this molecule that is going to show up as an individual hydrogen. Otherwise, integration of 6 is a triplet, yeah, no. I would write down all of this personally. So, next molecule. Or pair of molecules, I should say. We've got 2 substituted cyclohexanes. We've got a 1,1,4 dimethylchloral cyclohexane. And don't quote on that name, I'm just making things up. Yeah, and a 1,3. So, what do you notice right off about these guys? What's going to be our major difference here? Major difference is going to be that this guy has a plane of symmetry, and this guy has no plane of symmetry. So, which one would you expect to have fewer signals? This guy, plane of symmetry. No plane of symmetry equals beaucoup signals. So, HNMR, we've got our methyl groups here, which are going to be singlets, because they're not talking to anybody. And next over, we've got 2 hydrogens here that are going to be triplets, because they're only talking to these 2 hydrogens here. And then we've got another 2 hydrogens, which are also going to be a triplet. Now, if you are very familiar with the way HNMR works, you should be thinking to yourself right now that these hydrogens are going to be further downfield, meaning bigger number, than these 2 hydrogens here. You can put that if you want. And then finally, we have our hydrogen here, who is going to be in the furthest downfield of the block, and he's going to show up as a triplet. Okay, CNMR. Count everything on the plane and to one side of it. So these 2 methyl groups are technically on the plane. And depending on how picky you want to get, you can count them individually. And you could technically have counted them individually for the HNMR as well. What's going to make them different or the same is going to come down to how fast this chair is interconverting between its 2 chair conformations. Because if it's not interconverting at all, you're going to see one of these methyl groups show up as permanently axial and the other one show up as permanently equatorial. If it's rapidly flipping between the 2 chairs, they're going to equalize and show up as about the same. So you can write that down if you want. I'm sure that he's going to be impressed if you write all that down, but then again realize that they don't really like to read long novels. So, depending on how you want to count it, we can say that these 2 are the same, because we did that for the HNMR, so let's just be consistent. So you got 1 signal, 2 signals, 3, 4, 5. 5 total signals. IR. Well, there's nothing here that I would really pick out. Nothing here that strikes me as being very strongly different. Honestly, it's only the last pair of molecules that's going to have a big difference in the IR. Let's see what he says. Nope, he doesn't have anything about IR either, so don't worry about it. Okay, go down here. So, got no symmetry. For the sake of simplicity and getting a fairly fast answer here, let us again say that these this cyclohexane is going to be rapidly interconverting between its chair conformers, which means that we can count these two methyl groups as being identical, or closely enough identical that we don't have to worry about them being terribly different. Again, if you want to put in the fact that if one chair is favored over the other, and if you want to be terribly all for it, you can actually go draw the chair conformers and figure out if one chair is going to be preferred over the other chair. Hint, it is. But for the sake of simplicity, let's just say that they're going to be identical. So methyl groups can have an integration of 6 again, and they're still going to be a singlet. So that's not going to help us tell these two apart. Got 2 hydrogens here, and they are talking to 1 hydrogen. So integration of 2, that is going to be a doublet. Oh, sorry, I've forgotten. These guys up here are not going to be a triplet. They are going to be a doublet of a triplet, or if you want, a quartet. That's my bad. Okay, so moving on, this guy here is going to be our farthest downfield hydrogen. Integration of 1, and he is going to be a quintet. These guys here, integration of 2. They are going to be, again, doublet of a triplet. Moving on, these guys, you can count it as a triplet of a triplet, or you can count it as a quintet. Functionally, it's going to look most like a quintet. It's not going to be exactly a quintet because they are slightly different. Well, okay. I'll get into that a little bit later. So, these guys have an integration of 2, and they're going to be a quintet. These guys here, again, integration of 2, and they're going to be a triplet. So, you'll notice what mentioned before, that this has fewer signals and this has a lot more because of the lack of symmetry. Realize that these are chairs, and because you do have distinctions between the axial and equatorial positions, it's not going to be anything like as nice and neat as I've laid it out here with doublets and triplets and whatnot. Most likely, this is going to show up as a huge mess. So, if we're being completely honest here, this is going to show up as an absolutely huge mess, and this is going to show up as a lesser mess, but they're both going to be a little bit messy. So, CNMR, again, no symmetry. We're going to count for right now these two methyls as being equivalent. So you have 1, 2, 3, 4, 5, 6, 7 types of signals. This question is perhaps, I don't know. This particular pair of molecules gets a little bit complicated in terms of telling them apart. Your best bet for these is going to be your CNMR, because your HNMR is going to be a mess either way. Just as a hint for if you have to solve something for lab or whatnot, and you see an absolute mess in the HNMR, most likely it's probably going to be a cyclohexane of some sort. Okay, third pair of structures. And you will notice that these pairs of structures are essentially identical to our first pair of structures. And you can't even see half that molecule, I apologize. Okay. So you'll notice that they have exactly the same base carbon skeleton as our first pair of molecules. We've just thrown a bit of a wrench in here by putting in our deuteriums. What does this mean? Well, it does actually mean quite a lot, because what we have done is tossed in stereochemistry where we did not have any before. Also, important point, deuteriums don't show up at an H NMR. They are still H's, but they're not magnetic in the same way, so we don't need to worry about them at all. Which, to some extent, simplifies things. So, we have stereochemistry. Where's our stereocenter? This molecule, where's the only carbon that has 4 different things? It's going to be this guy here. He doesn't have an H. So you should be thinking, well, why on earth does this matter? It matters because of our enantiotopic diastereotopic stuff. By having a stereocenter in this molecule, we have induced these 2 hydrogens to stop being enantiotopic, which they were in the previous pair, just be diastereotopic. Because that's essentially how you tell if something is diastereotopic. If 2 essentially identical hydrogens are on a molecule that has a stereocenter anywhere, preferably closer, because the closer it is, the bigger difference you're going to get, they become diastereotopic. And we'll get more into that later when we get to the problem where he actually asks us about diastereotopic and antiotopic stuff. So, these 2 hydrogens here, instead of showing up as a single signal, are going to show up as 2 different signals, and they're going to couple to each other. Let's start in the same place we did for the first molecule, though. Let's start with this methyl group here. He's going to have an integration of 3, and he's going to be a singlet, because he's still really not talking to anybody. Okay, now we move over to our diastereotopic pair. They're going to be relatively close to each other, but they're definitely not going to be the same signal. So each one is going to have an integration of 1, and each one is going to be a doublet of a quartet. This is one that you can absolutely not simplify down to say that it's going to be a quintet, it's got 4 neighbors. Because the coupling to a diastereotopic proton is huge. It's extraordinarily large. It's one of the largest couplings you will see. And so therefore it's going to be very different from any other couplings you'll have, and they're not going to kind of blend together. So each of these guys is going to be a doublet of a quartet. And our CH3 on the end, he's going to have an integration of 3, and he is going to be a doublet of a doublet. Again, his coupling to each of these things is not going to be the same. So they show up as very different protons. They have very different coupling constants. So he has to be a doublet of doublet. You cannot simplify him down to a triplet. Realize that as you move a doublet of doublets closer to each other, they'll eventually overlap and become a triplet. So if these 2 couple to this methyl group in about the same way, it will show up as something that looks vaguely like a triplet anyway, but you should be aware that it's not going to be a triplet. Not in reality. Which is another huge discussion, because there's a school of thought that says there is no such thing as triplets anyway, every triplet is just a doublet of doublets. But, simplicity's sake, we like to talk about multiplets. CNMR. Now, in the first pair of molecules, we did have a little bit of localized symmetry where the 2 methyl groups were the same. We don't have that. No symmetry whatsoever, nothing, nada. So, every carbon is different. 1, 2, 3, 4, 5. Our IR, we're going to have an OH peak. And if you want, you can say that we're going to have a single peak representing this CH coupling. Sorry, CD coupling. Second molecule here. If you'll recall, our first pair of molecules, the analog of this guy had a plane of symmetry, and he was fairly simple to categorize. This guy, no symmetry. Also, this guy has a stereocenter. Where's that stereocenter? Right here. Which means what are we going to have? Diastereotopic hydrogens. Which ones are going to be diastereotopic? These guys. Okay. So, starting from the outside edges and working in, we've got this methyl group and this methyl group. They're each going to have an integration of 3. They're not the same thing because we don't have any symmetry anymore. He is going to show up as a singlet. He is going to show up like our guy up here, as a doublet or doublets. Deuteriums don't show up, so let me just worry about our stereotopic guys. As before, they're each going to show up with an integration of 1, and as before, they're going to show up as a doublet or quartet. Guy in the center is a D, and so we don't have a signal for him. So that's it! Ta-da! He ends up being actually just about as simple as he was before. So, moving on to our CNMR. Again, no symmetry, everything is different. 1, 2, 3, 4, 5. And he's going to have an OH peak in the IR, and if you want to get kind of splitting hairs, I would say that there is going to be 2 or 3 different CD stretches here. I don't know enough to tell you if that's going to be something that's going to be readily obvious for this. So, me personally, not knowing if this is going to be a significant of enough difference, I would not put it on an exam. Let's see if he mentioned it at all. And he doesn't say anything. His comments are mostly about the mass spec of this. Which, I suppose he did mention mass spec for all of these guys, and I don't know, my forte is not the mass spec, and I hadn't been thinking about it the whole time, so maybe I'll go back and, for each of these guys, make a comment on that. But for these 3 types of spectroscopy methods for this pair of molecules, HNMR is going to be your biggest assist here. But, as you can see, it's not that much of an assist, because each of them has 2 signals with an integration of 1 that are a doublet of quartet, and they each have 2 signals with an integration of 3, 1 is a singlet, 1 is a doublet or doublet. So that's not going to help you terribly much. That's why his answer for this one is relying entirely upon mass spectrometry. If you want to know what he's talking about, is mostly how easily things get knocked off. And I believe what he's saying is that the OH have differing levels of how easily they are knocked off. This OH is on a tertiary center, which means that it's fairly okay for him to leave, it's fairly stable for him to leave. This guy is on a secondary carbon, and so it's not going to leave as readily. So you're going to see the fragment representing this chunk of it a lot more prominently for this guy than you would see it for this one. Okay. Final structure. Pair of aromatic rings. Aromatic rings are always fun. And this guy is where our IR, which is apparently one of the hardest sentences in the universe to say, is going to come into play. Because you should notice right off that there is a major difference between these two in terms of our most prominent IR signal. And what is that? That is, of course, the OH. This is going to be your biggest distinguisher between these guys. So, he's going to have an OH, and he is going to have no OH. Right off the bat. And in terms of its strategies for taking exams, it's a particularly good idea that if something is very easy and right there and whatnot, write it down. Because if the other stuff is a little bit more complicated or takes longer or whatnot, you don't want to chance that you'll forget to write down the easy thing or run out of time to write down the easy thing. And therefore lose points. So, H&MR, we've got a tri-substituted benzene here, which is going to have 3 signals in the aromatic region, which is the 7, 8. This guy is only di-substituted, which means that he is going to have 4 signals in the 7, 8 region. I apologize, my format has apparently changed. Meh. And then this guy is going to show up essentially the same for both of them. C&MR, we're looking at the same sort of thing. But we have 1, 2, 3, well, okay. In either case, we've got a lack of symmetry here. So 1, 2, 3, 4, 5, 6, 7 signals, and 6 of them are going to be aromatic, which is the 120 region. And one of them is going to be a ketone, which is going to be up about 200. This guy, exactly the same thing. We still have 7 signals, and 6 of them are aromatic. And one of them is in this case, he's not going to be a ketone. He's going to be an ester, which pulls him down a little bit. He's going to be down closer 170, 180 region. So, if you want, that's a difference. And I think it's 150 to 180. 190 rather. Okay, so H&MR, 3 in the aromatic region versus 4 in the aromatic region. C&MR, our main difference is going to be this ketone versus an ester. And IR is going to be OH versus no OH. So out of all 4 pairs of compounds, this is the easiest one to tell apart. You could look into mass spec, and that's going to be mostly, you're going to have an ion here for the H getting knocked off, or you're going to, and in both cases you'll have the CH3 knocked off. I wouldn't worry about it terribly much. The mass spec was mostly for that 3rd pair of molecules, which were not readily apparent any other way. Okay, 3rd question, and those of you who know me know that this is one of my favorite things. Fairly straightforward. Treat it as a sort of intellectual puzzle like Sudoku. Also, this is, for those of you in lab, pretty much all you're doing. Okay, place to start. Those of you with experience with his exams from last year should realize that if he says hint, do it. So let's start there. You should know, and if you don't know, he gives it to you, the equation for finding the degrees of unsaturation. So 2 times the number of carbons, plus 2 minus hydrogens, and minus halogens and plus nitrogens, but because our formula here doesn't have that, we don't need to worry about it. Divided by 2. So that's going to be 2 times 5 plus 2 minus 10. So these guys cancel out. We're going to have 2 over 2. We have 1 degree of unsaturation. That means 1 ring, 1 double bond, 1 something. I'm going to write that up here. Set it aside, we'll come back to it as we need to. Okay, what else does he tell us? He tells us that there is a strong absorption in the range of 1700. What does that mean? That means a carbonyl. So, we're going to say, we know we have a carbonyl. And that takes care of our degree of unsaturation. Let's subtract a carbonyl out of our formula. This is a very good bookkeeping strategy because it helps you keep track of what you have and what you have left to figure out. So, C4H10O. Let's look at our H&MR spectrum, which I have put into the sort of table format that I find very useful for figuring these sorts of things out. some of these are going to be a little bit interesting, but we can say right off the bat, we have this guy here is an isolated methyl group. So he's going to be a CH3. Let's subtract that out of our formula. And down here, we've got another one. Isolated CH3, that is. Yes, we can get data out of what their chemical shift is, but we're not going to look at that right now. We're just trying to figure out what pieces we have, and later we'll use the shift information to tell us where they go. So we have another CH3. Subtract it out. Okay, so now we've taken care of our two CH3s. We've got our two CH2s left to take care of. They're both a triplet, so right off the bat, what this should tell you is that they are coupled to each other, because there's literally nothing else for them to be coupled to. Subtract our ethylene out, and we're left with just an oxygen, which tells us, hey, we've got an oxygen. Those are all of our pieces. Count them. 1, 2, 3, 4, 5. 5 pieces. That's taken care of our entire formula. You should get to this point before you start trying to put things together. Okay, having gotten to this point, what do we look at? We look at the fact that these two are both isolated, and that they have significantly different chemical shifts. One of the numbers that I know in terms of chemical shifts right off the bat is anything in the vicinity of 2 is attached to a double bonded carbon. So I'm going to guess that this methyl group here is attached to our carbonyl. So I'm going to take away our bookkeeping, and I'm going to say that this guy plus this guy equals that. Okay, so that takes care of that piece, and that takes care of that piece. We now have another isolated methyl group. We've got an ethylene and we've got an oxygen. Can we stick our other methyl group onto the other side of the carbonyl? No, because then we wouldn't have anywhere to stick these guys. Can we stick our methyl group onto the ethylene? Some of you might be tempted to try this. You should pay huge amounts of attention, though, to the fact that this guy is a singlet. He absolutely cannot be attached to our ethylene, because if he were, he wouldn't be a singlet. Now, where does that leave him to be attached to? Our oxygen. Does that make sense? Look at the chemical shift. What is this in the region of? And this should be something that you are familiar with. You don't need to know exact numbers, but generally anything between 3 and 4 does make sense for hydrogens attached to a carbon attached to an oxygen. So, we can put these two together. And at this point, there is no other way we can put this molecule together. Our ethylene has to be attached to our carbonyl on one side and to our oxygen on the other side. And voila, your molecule. Okay, so problem number 4 is one that I found actually a little bit tricky. This is one of those questions that is easy enough to approach if you know the basic ideas behind things about what's going to make a benzene attacking, about what's going to be more reactive, a benzene or an alkene, and so on and so forth. He says that this is actually a problem from your text, which means that, like as not, you should have seen this before and it should be somewhat familiar to you, but I'm going to approach it as if you had never seen it before, as a kind of how to figure things out if you don't know where to go, if you haven't seen it before. So, I don't know if he gave you the structure for styrene. This is it. styrene you might know from real world applications, the styrofoam and all that. It's a polymer, and the reason that it's a polymer and it's such a good polymer is this benzylic alkene here is very reactive, and it's, if you give it the right conditions, it'll be very reactive on itself, which is actually precisely what we want it to be doing here. Because you'll note this guy's got 8 carbons, and we end up with 16 over here. So we're sticking 2 of these guys together somehow, some way. So how do you figure out where to start? You know that you're given an acid, and acid's a good electrophile. It's going to get attacked. What's going to be doing the attacking? And I will be physically pained if you guys try and tell me that it's going to be our benzene. Because at this point you should know that benzene doesn't have any real double bonds in it. And if you have an actual real double bond, that's going to way trump in nucleophilicity anything a benzene can do. Benzene is aromatic, which means it likes to sit there and play with itself. So let's use our alkene, our actual alkene, to attack our acid and see where that gets us. Question now, where is the plus charge going to go, and who's going to get the H? If we put the plus charge here, it's going to be primary, which we know is a really bad thing. Can be leavened if it's next to a pi system, but in this case it's not. This guy is secondary and benzylic, which means that he is where our positive charge is going to go. Because a positive charge is stabilized not only by substitution, but also by resonance. So, your familiarity with electrophilic aromatic substitution should tell you that one of the things that will make a benzene want to attack something is if it has a carbocation, which we've just generated. This should prompt us to bring in our second styrene that we've already decided needs to be there because we our chemical formula up here. Again, we have exactly the same issue as we had in the beginning in what is going to be attacking our electrophile. Our electrophile is changed to a carbocation, but the question is exactly the same nevertheless. So, while we do know that a carbocation can induce a benzene to attack, our benzene still has an intact alkene, which, as we said before, is far more nucleophilic than anything the benzene can do. So who's going to attack our double bond, or our carbocation? It's going to be our double bond, and not our benzene. Where does this get us? And this is absolutely a case of where you should be counting your carbons and keeping track to make sure you have enough. So 6, 12, 13, 14, 15, 16. Always good to check. And again, our carbocation went here for the exact same reasons that it went here. What do we do now? We do an elimination. Because obviously we don't want this carbocation to stay there. Your other option would be to have the water directly attack the carbocation itself. But in this case, if we do an elimination, we add back in an alkene to our aromatic system, which does the resonance will beat out the stability of an OH every time rather. Okay, so now we have an alkene. He's got 6, 12, 13, 14, 15, 16, 5, 10, 11, 12, 13, 14, 15, 16, C16, H16. this is probably A. So, the question is, what are B and C? And how do we get to them? Sorry, coffee break. Okay, so we still have an alkene, it's still in acid. I'm going to redraw our A and realize that A has cis and trans conformations. I'm going to redraw A up here. So, as we said, this is an acid. So it's actually going to be in equilibrium with the carbocation that was right before A. Which, the way that you would get there is by taking some more acid. And this means that our plus charge can go to either one of those locations. Well, it doesn't actually. The one is benzylic and the other one is just secondary. So our carbocation is going to be pretty solidly there. What do we do now? We could go back to A, or we can have a benzene attack it. Because, as we said before, one of the things that will rouse the benzene out of its self-contentedness is a carbocation. We cannot use this benzene to attack it because it's right there, but we can use this benzene to attack it. This is a stereocenter, just bear that in mind. And whatever it is, it will always be. So that you're actually going to have a mixture here of it being up and down, a racemic mixture if you like. But at this point, we can use either this bond to attack it, or we can use this bond to attack it. Why don't we want to use this bond? Because if you do a para attack on this carbocation, you're going to end up with a really large and weirdly bonded bond angle that doesn't match with our sp2 bond angles well enough. And it's also generally a rule of thumb that if you have an intramolecular reaction that can make a 5 or 6 membered ring, that reaction is preferred over anything bigger or anything smaller. It's mostly a sterics issue. So, we can attack it here, we can attack it there. One, two, three, four, five membered ring. With the benzene sticking off of it. Very terribly dropped benzene. And then you'll just get an H removed to send that guy back to his aromatic self. And again, 1, 2, 3, 4, 5, another 5 membered ring. With the benzene sticking off. apologize for that. That was ridiculous. It shouldn't be there. Okay. These are our two guys. Whatever the stereochemistry here was, it'll stay that way. What we've done is introduced differing stereochemistries at this analogous center. Which means that these two are a pair of, well, actually it's a lot of things, but what we're looking at is one diastereomer and another diastereomer, and each diastereomer is a mix of enantiomers. And that's your compounds B and C. If you want to have the stereochemistry drawn out, you can do that. So for kicks and giggles, let's draw out what we get. Let's say that this guy was wedged forward in the first place. When we flip him upside down, he's still in exactly the same stereochemistry, but because we flipped him, we need to draw him in the opposite looking stereochemistry. This guy is 1, 2, 3. He's an R. He's still an R here. 1, 2, 3. But the H is forward, so it's flipped. So he's still R there. I'm going to make this some arbitrary stereochemistry here. And you will see our pair of diastereomers. The easiest way to think about them is cis and trans. Realize that your final answer should not have this plus charge here, that you should take it down to the aromatic compound, but that's the basic idea of what's going on here. Biggest things to remember is that an alkene is extraordinarily much more nucleophilic than a benzene. The benzene will only come into play after you've exhausted all of the actual proper alkenes. That's your answer. It doesn't matter which one of these are B and C. You can label them arbitrarily, or just write the pair of them and underneath write B plus C. Doesn't matter. Okay, this problem is fairly straightforward, and most of it actually relies upon your ability to determine each H as being one of a diastereotopic pair, one of a homotopic pair, or one of an enantiotopic pair. So let's go through that. I will put up another video going through briefly what makes something, each one of those things, kind of like a back explanation of why on earth we are concerned about all this. So, first compound. Got these two H's here. So we are concerned about whether or not they are going to be diastereotopic, homotopic, enantiotopic. How do we determine that? We look for a stereocenter. This molecule has one. So, that means that these two H's are diastereotopic. Which means, in brief, that if you replaced one of them with something else, your resulting pair of compounds would be diastereomers. More on that in the other video. So, because they're diastereotopic, they are non-equivalent and will couple to each other. Which means that this guy makes this hydrogen show up as a doublet. These three will make it show up as a quartet, and this one will make it show up as a doublet. So overall, this guy's going to be a doublet of a quartet. Moving over to our second compound. We no longer have to worry about another H on the same carbon. What we have to worry about is this constitutionally symmetric hydrogen. What's going to influence this is whether our molecule here is chiral or whether it is achiral. How do we determine that? You can go through and look for plane of symmetry, point of symmetry, that sort of thing. I find it is a bit more foolproof to go through and just assign R and S to things, which is, of course, your favorite thing, but you do it a lot and it just kind of will flow naturally and you learn the shortcuts to it. So this stereocenter here, first priority is obviously the bromine, fourth priority is obviously the hydrogen. This carbon has more things on it than this carbon, so we've got second and third priority. So he's going R, the fourth is in the back, which means it is what it looks like. He is R. This one. You'll notice that it has all exactly the same substituents on it. So you don't even have to worry about what's going to be 1, 2, 3, 4. You just copy what you did over here. 1, 2, 3, 4. He's going R, and our 4 is in the back, so he is what he looks like. He is R. So what does this mean? That means that this compound is chiral. Because one of the hallmarks of a meso compound, an achiral compound with stereocenters, is that one center will be R and one will be S, mirrored across your plane or point of symmetry. This guy is chiral, which means that if we replaced this hydrogen with something else, say a D, so that we can keep our priority levels, what your resulting pair of compounds will be are identical. You replace this with a D, you still have RR. You replace this with a D, you still have RR. That means that these two hydrogens are homotopic and do not couple. Which means that the only thing that the circled hydrogen is coupling to is the CH3. Which means he's just going to be a quartet. Our structure up here, same sort of issue. And again, if you want, look for a plane of symmetry, look for a point of symmetry. In this case, because you've done this compound, which is an isomer, you don't even have to assign priorities. You can say, this stereocenter is exactly the same, has not changed, which means he has to still be R. And this stereocenter, all the same things, but you flip the BR and the H, which means it has to be S. This compound is achiral. What does this mean for us? So let's go through and replace the H's with D's again, so that we can keep our priorities and keep our R and S designation. We replace this guy with a D, he's still R, he's still S. Okay, cool. If we replace this guy with a D, he's still R, and he is still S. Okay, but what is the relationship between replacing this H versus replacing this H? Your compounds are now enantiomers, because if you replace this guy, then the compound with the D is R and the compound with the H is S. But if you replace this guy, the compound with the D is S, and the compound with the H is R, which means that they are enantiomers. Which means, of course, that our H's here are enantiotopic. However, this doesn't change terribly much, because enantiotopic hydrogens don't couple either. They are, within the eyes of the HNMR system, identical. So, the only thing that we have to worry about coupling to is this guy, which is going to make him a quartet. So that is my take on this first exam that you've had in 273. If you have any more questions or any comments or anything, feel free to email me at nisa@hawaii.edu, at which point, if you so desire, you can request a Skype conversation. I apologize for the inferior quality of this. I'm just trying to get some bugs worked out. If I have done anything glaringly wrong, please feel free to let me know, and I'll see if I can make a correction. Thank you.